So today we're going to look at our second set of notes in chapter 1, which is going to be over graphs. Now we should have seen lots of different types of graphs in the past. Today we're just going to look at some different characteristics of function graphs. In our next section we will look at specific graphs of our parent functions and how we graph given an equation. But today we're just looking at properties and characteristics. So our first thing that we're talking about is domain and range. So remember, when we're talking about domain, we're talking about x values, and we're talking about range, we're talking about y values. And we can find domain and range given a table, given a graph, given an equation. There's lots of different representations that we can see, and we should be able to find our domain and range from any of those. So in this case, it says use the graph of the function shown here to find the domain of f, the function values that they give us, and then the range. So our first thing we want to look at, like it said, we want to state our domain. Now remember that our domain is going to be any x value that we can plug in. So notice that we're talking about x's, which is our horizontal axis, and we start at -1. So that's going to be the first value, and we're going to give it a hard bracket or a square bracket because that means that that number is included or that it can be equal to. And you say, well, if I'm looking at the graph, how can I tell if it can be equal to that or not? It's pretty easy. Notice that I have a closed circle. If I have a closed circle at that value, that means that that number is included. Now, as we go across, we have points, we have points, we have points, we have points, and we go all the way to where our graph stops, which is going to be at 5. So I'm going to do comma 5. Now, hopefully we notice that this time I have an open circle, which means that 5 is not included in our domain. So I'm going to put a parenthesis. Now we can get as close as we want. We could do 4.99999, and that is going to be included in our domain. It's only 5 that's not. So that's our domain. So then on part B, it asks us to find f of -1. Now remember that if I'm looking at inputting a -1 and I'm wanting to find the answer of that, I'm looking for the output, which is also our y value. So in this case, I want to look and see what is the associated y value for the input of -1. So I go to -1 and I see what is my y value, and it is 1. So then again, I'm looking at f of 2. I'm going to go over to 2. I'm looking for what is my y value. It is -3. Now they didn't ask us to find this, but let's say they did. What would happen if I asked you to find f of 5? Now some of us might automatically say, oh, it's 2. Be careful though, because remember that this is where that point would be. However, it's an open circle, so I can't actually plug in 5. So f of 5 would be undefined. And then lastly, it asks us to find our range. And remember, our range are the y values that we can be between. So notice that all the way at the bottom, we're at -3. And again, we're looking vertically this time, because that's our y values, to make sure that we don't have any holes or any gaps. Notice that we do have this hole here at 2, but I have other points that kind of fill that in, so I don't have to worry about it. And then we go all the way up to 3. So our range would be -3 to 3. Alright, so next up, it asks us to use the vertical line test to determine whether two things are functions or not. So we kind of talked about this in our last section, and we didn't quite get into it a ton in depth. And so this time we're actually looking at some graphs. So notice that they've already drawn a vertical line for me, which is a little helpful. And on our first graph, notice that that line goes through 2 separate points on that same vertical line. So if it hits 2 points on the same vertical line, that means that it is not a function. It does not pass our vertical line test. Notice on our next one, This one does pass our vertical line test. No matter where I go, no matter where I draw a vertical line, I would only ever pass through one point. Now the last one is a little bit tricky, so be careful. Because notice, I'm okay as long as I'm on the left side. I'm okay as long as I'm on the right side. But the middle part is what's a little bit confusing. We have to go back to that definition. So does that vertical line cross through more than one point? And the answer is no, it doesn't cross through more than one point. It doesn't cross through any point, but it doesn't cross through more than one point either. So it would still pass our vertical line test, so it is still a function. Now, that graph would not be continuous. So remember that in order for something to be continuous, I have to be able to use the entire graph or draw the whole graph without picking my pencil up. In this case, we couldn't do that. We have to have that jump in the middle, but it can still be a function and not continuous. All right, so next up, we're looking at the zeros of a function. So we did talk about a little bit last time about setting a function equal to 0, so that can allow us to find zeros. But let's give a definition for what that actually means. So zeros are going to be any value that makes a function equal 0. Now, some other words that we may hear used are also going to be roots. They can also be called our x-intercepts. And they can also be called our solutions. So all of these words are going to mean the same thing. I'm looking for what x values are going to make the entire function equal to 0. So it says find the zeros. All right. So again, hopefully we recall that in order to find the zeros, I'm trying to make my function 0. So I want to plug that 0 in for f of x. And then we need to solve for x and find out, okay, what x values make me get 0. So on our first one, we have a quadratic. So we can't just start subtracting or adding or trying to do opposite operations. Remember that we need to first try and factor it. So I have a 3x squared plus x minus 10. I notice that my a is not 1, so I'm going to use the AC method. You can use another method. Just make sure that you're using correct mathematical steps. So I would multiply 3 by negative 10, which gives me negative 30. So I'm looking for two things that multiply together to give me negative 30, that add together to give me positive x. And so that would be a positive 6x and a negative 5x. And then I'm going to factor by grouping. So I can factor a 3x out of my first two. And we can factor out a negative 5 from our next two. Again, we're using factoring now to help us solve. So if we're still struggling with the factoring itself, we need to make sure that we're going back and looking at those previous notes, coming and talking to me if we need extra help. So now that I have it all factored, remember that we can then set those factors equal to 0 separately. And then solve. So we get x equals negative 2 and x equals positive 5/3. So in this case, our function has 2 zeros, which is all right. So in our next one, we need to figure out, okay, where does the square root of 10 minus x squared equal 0? And we need to be a little bit careful because we have a radical and we have things that are being squared and such underneath it. So if we have the square root of 10 minus x squared, and we want to now set that equal to 0. So in order to solve, I first would want to square both of my sides to get rid of that radical. Well, what's nice is 0 squared is going to be 0, so I would end up with 10 minus x squared equals 0. So we could then add x squared to both sides. And then we're going to take the square root. But remember that whenever we take the square root, we need to add plus or minus. Now I did say we need to be careful because we have a square root. We need to make sure that whatever number that we get as our answer is going to be in our domain. So I get the square root of 10. So if we were to take the square root of 10, we get 3.16 approximately. So if we were to take that in there and then square it, we would just want to make sure that we wouldn't get a negative. Well, square root of 10 squared is going to give me a 10, then 10 minus 10 gives us 0, which is fine. But if we were to plug in the negative square root of 10, we just need to make sure that it also works. But if we square that negative, it becomes positive 10 as well. And so again, we would be okay. All right, and then lastly, we have h of t. Again, we're looking for our zeros. So the thing to remember about your rationals is that your denominator can't be 0. So we know that we can't get any zeros out of the denominator. So that means that the only place that we can have things being equal to 0 is going to be the numerator. So I set my numerator equal to 0, and then I'm going to solve for t. And that would be my answer. All right, next up, we want to talk about some different types of graphing properties. So we can have increasing, decreasing, and constant graphs. So a graph is basically increasing, most of us would say, when it's going up. The problem with that definition is that it doesn't really say what it's going up in regards to. I could be going up to the left, up to the right, and then it matters on your perspective as far as what left or right means. So we need to come up with a better definition. So the way that we have stated it mathematically is a function is increasing if and only if. So that's what the double F means, is if and only if, for any x1 and x2, x1 is less than x2, then f of x1 is less than f of x2. So basically what we're saying is as my x values go to the right, my y values must also be going up. And so it gives us that context. Now, in order for it to be decreasing, basically everything is going to be the same, except instead of our y values wanting to go up, we want them to go down. So we would say that f of x1 has to be bigger than f of x2. And then lastly, for a constant, basically again, everything is going to be the same, except instead of going up or going down, we want them to stay the same and be equal. Now let's look at what that means graphically. So it says use the graphs to describe the increasing and decreasing behavior. So here, I'm looking at the function x cubed. Now it looks like my function is going up for the most part. The problem that we run into is there in the middle. It's kind of hard to tell what's happening. And so what we can try and do is pull up a graph either on Desmos or on a graphing calculator. I'm going to go ahead and pull up Desmos. That way we can maybe zoom in and see a little bit more of what's happening. So I want to look at the function y equals x to the third. And it gives us the shape that we were wanting it to have. So if we look at this, we're trying to look at that point 0, 0. Let's zoom in. If I keep zooming in, and we notice that it kind of starts to level off, but notice here that my y values are still increasing. They're still getting bigger. Now, they're getting bigger really, really slowly, and here it looks like they're all 0, but that's just because it can't round that far. They are increasing just really, really, really slowly. But that means they're still increasing. So we would say that this graph is increasing from negative infinity to positive infinity. And then it's not decreasing or constant anywhere. Now our next one is a little bit different. So notice that we're going up, or it's increasing. Our y values are getting bigger from negative infinity all the way until we get to this point right here. Now this point right here is at -1, 2. But we need to be careful how we talk about it, because notice that if I were to use my y value, which is 2, we could be talking about this point, but we also could be talking about this point over here. And we only want to be able to talk about one point at a time. So instead of using a y value, if we use the x value, I can only be talking about one point because it is a function. Now notice that we also go back to increasing once we get to 1, and then it continues to increase forever. And then we're going to be decreasing in between those, so between -1 and 1. We want to use parentheses for everything, because notice at a specific point, we're not going to be increasing or decreasing, so we don't want to include that value. We just want to say that it changes at that value. So notice here, I am increasing from negative infinity all the way until we get to 0. We're going to be decreasing from 2 to infinity. Again, remember that I'm talking about x values. So even though this is going down, I'm talking about my x going and getting bigger and bigger and bigger, which is why I use a positive infinity, not a negative infinity. And then it is constant in between those two, so 0 to 2. And that's how we would want to label any of our graphs when we're trying to say if something's increasing, decreasing, or constant. All right, next up we have what's called our relative mins and relative maxes. Now we've probably heard of minimums and maximums, but we might not have heard the term relative mins and maxes. So basically it's going to be a minimum or a maximum for like most of the graph, for a part of the graph. So it says AF of A, so just some y value such that for any x in the interval x sub 1 to x sub 2, f of A has to be smaller than or equal to f of x. And again, basically our relative maximum is going to follow a very similar format, but now instead our f of A needs to be bigger than all of our other things. And then something important to point out is that these are going to be called turning points. So that's another way of thinking about it. When our graph turns from increasing to decreasing. So let's go back to our previous example. So notice I'm going to use this second graph that I have right here. Okay, so we should notice that we have two spots. that could potentially be relative mins and maxes, because that's where the graph is going to turn. So in this case, notice, give me a bright color. So I have a point here and a point here. So notice that if I were to like chop off part of my graph from like here to here, notice that that is going to be the tallest point in that region. Now it's not the tallest point overall, because notice that this part of the graph still goes up forever. And again, if I were to chop off part of my graph, this is going to be the smallest point in that one part. It's not the smallest point overall because this part goes down forever. However, it is a relative max, meaning relative to that part of the graph, and a relative minimum, meaning the smallest part of that part of the graph. And so that's why we can also think about them as turning points, because notice that we turn from increasing to decreasing or decreasing to increasing. So it says use a graphing calculator or utility to approximate the relative minimum of the function given by f of x equals 3x squared minus 4x minus 2. So I'm going to go back to Desmos. So we want to use the function y equals 3x squared. It says minus 4x minus 2. And so we should end up with a parabola. I need to zoom out a little bit. I'm super zoomed in right now. And notice that we get a parabola shape. So it looks like a U. And notice that the turning point is going to be where this parabola changes from decreasing to go to increasing. And it's at approximately 0.667, comma, negative 3.333. Now, if I asked you for the absolute max or the absolute min, I'm asking for the overall smallest or largest. And for that graph in particular, we would not have an absolute max or min, because notice that it doesn't, or sorry, we would not have an absolute max, because notice it goes on forever. And in this case, our relative min would also be our absolute min, because it's the smallest point overall. However, on the last one that we looked at, this here at 1, negative 2 would be our relative min, but it could not be our absolute min, because this part of the graph continues on forever.